Here we go.
I'm going to have to start using black for everything. I've noticed some recordings didn't come out too well with different colors. Okay. Chapter 13.
What was that? Oh, okay. No big deal.
Chemical equilibrium. All right. I'm sure I mentioned when we were working on kinetics, you have to do kinetics first in order to understand equilibrium better. Because kinetics deals with the underlying speed of the reaction. Although actually they're two sides of the same coin. Equilibrium looks like the reaction has stopped, it's not doing anything. But in fact, at the molecular level, there's furious activity. In fact, if these are our reactants and these are our products, it's not just going one direction. The reaction can always go backwards. Now, expressing the difference, whether this side is favored over that side, we can quantify that. But the speed of the reaction in the beginning, of course, if you only have reactants, everything's headed for products. If you only have products, everything's headed for reactants. But eventually, you get enough on either side that you have competing forward and reverse reactions. And those reactions match one another at some point, so that it looks like, from our perspective, the macroscopic world, that the reaction is stopped. And that's an equilibrium condition. Okay. For example, we'll react nitrogen and hydrogen to make ammonia. If this is our time scale and this is concentration, of course, we have some nitrogen and some hydrogen, okay, but no ammonia. So over time, the concentration of these two, the reactants, decrease and the product increases. And when we reach a point where they apparently don't change in concentration, that's our equilibrium position. So it all has to do with the rate of reaction. If you have you could have a reaction rate K value, right, for the forward reaction, but you'd have a different K value for the reverse reaction. Okay. But the rates would be the same at equilibrium. There's another way of expressing it. The forward rate, of course, is very high in the beginning, and the reverse rate is 0. That's why for studying kinetics, we always pick initial rates, because under these conditions, there's no competing reverse reaction to interfere with the study of the rate of the reaction. And at some point, the forward and the reverse rates equalize, and you have equilibrium. Okay, let's take this discussion in terms of qualitative assessment. So we have this reaction where we're reacting water and carbon monoxide to make hydrogen and carbon dioxide. And the initial conditions we're saying we're at equilibrium. Right? So the forward reaction and the reverse reactions are the same. You have some of this over here, and you have some of this over here. We're at equilibrium. So what would you expect to happen if we introduced more water into that situation? Any guesses? Is it going to stay where it is? I mean, we add more water.
Water in?
I'm sorry?
We add more water in?
Yeah, add more water.
No, I mean, it wouldn't stay the same if you add more water in.
Right, that's right. We've upset the apple cart.
Yeah.
It was balanced, now it's not balanced because we added more reactant. So what will happen? The reaction will shift this direction. It will consume some of this water and consequently some of the carbon monoxide, if there's any left, to make more product. And it'll keep doing that until we've reestablished forward and reverse rates equal again. Okay. Similarly, if we added more hydrogen, the reaction would shift back towards products, reactants. You add product, you get a shift toward reactants until you reestablish equilibrium again. Forward and reverse reactions have now stabilized at equilibrium. So we can quantify a mathematical expression of the equilibrium conditions. It's called the law of mass action. And it was proposed by two Norwegian chemists. And he doesn't look Norwegian, but maybe he is. He was this guy's brother-in-law. They worked together, Weyouch and Goldberg. You'll notice from the date that these guys were happily working in their lab while the Americans were killing each other. So they wanted to derive some sort of an expression. They wanted to quantify equilibrium and came up with the law of mass action. They called it chemical dynamics. This is the rate of reaction. Dynamics just refers to movement. Actually, dyna is a Greek prefix for power. So they wanted to, they were tackling this problem, chemical statics, which says that nothing's changing. And on a macroscopic level, that's true. Nothing is apparently changing. So the expression itself is in terms of concentration. So at equilibrium, we have concentrations of reactants and products, and then we can put those concentrations into an expression. And it turns out the expression is a constant, another K value. We make this one a big K, and the little k for, in the last chapter, was for rates of reaction. So big K's are for equilibrium situations. I don't like the way they do that. I prefer if we do this. And then we make our coefficients. Just little a's, little b's, little c's, little d's. Then the equilibrium expression is always the product of products divided by the product of reactants. We use square brackets. Square brackets automatically mean to any chemist looking at it, equilibrium. And whereas in the study of kinetics, we could not take these coefficients and use them in our expression, in our rate expressions. In equilibrium, we do use these coefficients. So once you've balanced your equation, then you use the coefficients as exponents. So C would go here, D would go there, little a would go here, go there. So that's your law of mass action. And these K values, you'll notice as we proceed, sometimes have subscripts to refer to particular types of reactions. This is the generalized form. Products over reactants. So, what would this expression look like if we just took the reaction and flipped it and made these the reactants, these the products? This whole thing would be flipped, yes. So the K of the reverse reaction would just be okay. Let's suppose that you look up this reaction, whatever it happens to be, in a book, and the reference manual gives you a K value for that reaction. But you need to use the reaction in the reverse. What do you do with that number that you're given? Well, if this is the reverse reaction, looks to me like this value is actually equal to the reciprocal of that value. Right? So that's what you do if you're given a K value. You need to use the reaction in the opposite direction. The K value then becomes the inverse of the K that's given you. Okay. If we multiply if we have to multiply this whole expression by some value, right, what does that do to the K value? This K value right here. It would be NA, right? So our new expression would be this. Let's see. Our new K. We would have C, A, D, A. That doesn't change. But N times A gives you a new coefficient. So this would be A would be N A, and B would be N B, N C, D. Okay, what do we know about exponents from algebra? Sorry? Mm-hmm. We can factor out the exponent. Then, if all the exponents are multiplied by n, then the whole expression is raised to the power of n. If we go back the other direction, that means this is that power, that power, that power, that power, to n. That's a valid algebraic transformation. So what does that mean? Well, remember, this expression right here is what? K. So it's K to the n. So our new K, we have to multiply our expression by n, a number, Then the new K is the old K to the nth power. Those are valuable bits of information when we get to work with the K values and we start combining equations. We combine equations, and maybe we have to do some transformations. We might have to flip it. We might have to multiply it by a factor of some kind. So we need to know how to do these things, what to do with the K values. Now, the last bit of information that's important is K values are usually written without units. Any idea why? There's some magical universal law that just says that, no, you can't write these with units. That's against the law. It's convenient. Look at what would happen. If this is molarity, that's molarity. All these are molarity. Then you raise this molarity to some power, raise that one to some power, which varies depending on the expression, right? You would have just a huge possibility for combinations of units of measure, right? So we just leave them out. And we take extra care that we write them correctly. Okay. If you look up the K values in a reference manual, won't have any units in it. Right. So if you do all your steps correctly, as we're going to do in a few minutes, then the units of measure are not important. So that just means that the calculations using K are not friendly to dimensional analysis. Any questions so far? Part of the board. Black doesn't just race as well as others. Okay. I think my son made this thing. He's 27. He was living like some of yours. Okay, that can't help himself. You have to know better. Stay away from me. So, also, if we hold the temperature constant, then the K is a constant always. The K will change. If you change the temperature, what are you doing to the rates of reaction? Right? You're speeding them up usually. You're speeding the rate forward and the rate reverse up, but the forward and the reverse rates now may not respond the same way. Right? So that changes the balance. So anytime you change the temperature, the K value changes. The temperature is constant, K is constant. Does not change. Now, I need to draw a distinction between equilibrium constant, right, or K, and equilibrium position. For a given temperature, this value is constant. That law of mass action fixes this value for that temperature. But if we start off with different concentrations, actual concentrations of reactants, actually, you start off with a concentration. It's not at equilibrium yet, so we use parentheses. If you start off with this concentration of reactants, then you'll end up with a certain concentration of products based on that value. But if you start off at a different concentration of reactants, you'll end up with a different concentration of products. Or if you're at equilibrium and you do something to disturb it, like we did earlier, like add water or add hydrogen, then the position changes. This is satisfied as a constant, but these concentrations may be different and still give you the same K. That's the equilibrium position. And the position can be anything. Right? We can change the position. All we have to do is just take away some reactants or products or add some. And we change the position. But this we do not change as long as the temperature stays constant. So this is constant, that's not constant. But they are related. Okay, I mentioned earlier that K values have subscripts that mean special things sometimes. And we'll encounter some of these. If we just put a K up there, a big K, we usually mean this one. Just what is the equilibrium constant? And it's usually in terms of molarity. Right? So your reactants and products are in concentration units of molarity. If all gases are part of the reaction, and instead of using concentration, we use partial pressures, right? Then we might give it a small p for pressure. So the Kp gives you a clue, since we don't report the units, it gives you a clue that the calculations were made using partial pressure. And then the partial pressure, it could be pounds per square inch, it could be pascals, it could be any number of things, millimeters of mercury. So that will also have a bearing on the value. Others that'll crop up from time to time is W is very special K for water dissociation. And we'll talk about that a bit later. Maybe not even in this chapter. Acids and bases, chapter 14 and 15. We'll get to the place where we use this one. Also, the stuff we're going to learn in this chapter, we're going to come back to it, revisit it in future chapters. Learning to do the equilibrium calculations is something we can't escape from now to the end of the chapter, end of the course. So don't learn it and forget it. If we have an acid dissociation, like gives up a proton, or if we have an acid like that, and the products are like this, right, then we can write an expression for that. And the K value will be designated with a little a. We'll get to a chapter where we're talking about solubility. Right? I'm not going to define it now, just be aware. SP stands for solubility product. There's also a formation constant, which is used for, actually we're going to do next week with our Le Chateliers, we're going to allude to formation constants. And I'll bring that up in the lab. But we're not going to, for that lab, we're not going to calculate them. That's later. Just need to be aware of what we're doing in that. And this is not by any means stretch of the imagination the only set. These are the most common ones. Okay. So in this case, here's an example. There's our Haber-Bosch reaction again. And if we write it as KEQ, equilibrium constant, it's going to be square brackets. And we'll have our proper exponents, right? 2, 3, 1, 2, 3, 1. But we could also, since these are all gases, write them in terms of partial pressure. When you do that, you don't use square brackets. you have this P value, which means pressure. And then you have the subscript for which one it refers to. But the exponents are the same. It's just that the values are different. So this Kp is not equal to that K, simply because we're using different units.
Why is NH3 squared? Did you already say that?
Right here.
Oh, yeah, it's right there.
Yeah. But they can be related to one another. In other words, if you know one, you can calculate the other one. But you have to use elements of the gas laws to do it. So let's see, what would the calculation be like if the equilibrium pressures of each of these gases now, once we're stabilized in terms of atmospheres, right? You have these values. You just set up your equilibrium expression, right? Products to the power over reactants to the power, and then plug in the numbers. Don't forget your powers. And we get this value. Now, it won't mean anything unless we know what the values, the units that were used to calculate it. But we can draw a conclusion from this one. Notice this value is huge, 39,000. That's 4 places to the right. 39,000 is the Kp. So what does that mean? That means for this reaction, the equilibrium is which direction? Far to the right or far to the left? Think about how it's calculated, right? Products on top, reactants on the bottom. So if it's a huge number, you would expect it to be favoring the products. Big numbers means a large K value means large numerator, small denominator. Likewise, if it were some other reaction that had a very small number, 10 to the minus 4 or something like that, then that says that the reactants are favored and the products are not. Simply related to the nature of quotients. So, if we know the K value, the equilibrium, and we know the this is an R value, and that R value has to be chosen with respect to the let's back up, with respect to these units. Right. So for simplicity's sake, let's just keep the Kp in terms of atmospheres. Then we can always use the same R. This is the first one you were introduced to, the R value, liter atmospheres per mole K. And then this temperature is in Kelvin, okay? This is your K value that you may have determined or may have been given. And then this is the K in terms of partial pressure in atmospheres, derived from atmospheres, I should say, not in atmospheres, because we don't know what the units are. But this would be derived from atmospheres, this would be derived from molarity. And then we have to figure out what is this delta N. Delta N is the change in moles. So if we know the coefficients of the gases only, and of course, if your reaction is all gases, then no big deal. Just use all of them. You take the coefficients of your, let's write the reaction up here. Say hydrogen. And ammonia. So 2, that makes this one 3. Okay, so what's the change in N? Well, the reaction, the products here, there's only one of them, so that's the total of the products. And then you subtract the sum of the coefficients for the reactants. So that's 3, and that's 4. That's 4. But the -2 is equal to a change in N. What that means is, between here and there, we decreased by 2 moles, right? This is 4 went to 2, so we decreased 2 moles. And it's okay to have a negative value. Right? Just be sure you don't forget that when you plug it in your equation, right? Because your calculator can handle negative powers. So that's how you calculate Kp derived from Keq. And of course, this is like any reaction. If you want to find out what K is, but you know this one, you just solve for the unknown. Okay, so here's an example. Here's an example of solving for K when you know Kp. And so Kp is given here. And there's the temperature of the reaction. So we use this constant. We use this value for temperature because we added 273 to it. And then we have -2 here, 2 minus 4.
Well, they write it that way instead of just putting -2 away.
To save a step.
Okay.
Yeah. Right. We could write it this way, and then we'd have to bring it down here and write the whole thing out again and put a -2 in there. Yeah. And then we solve for K. So we have this -2, that is the power of this expression. And then whatever that is, we divide it into this one. And that gives us K. So the previous one was like 10 to the 4th in terms of Kp, right? Yeah, 10 to the 4th. But in terms of molarity, K is 10 to the 7th. It's still the same reaction. It's just when we change the units. But it's also good to know if you got if your calculation gave you a negative power here after starting with positive, you're probably wrong. Because this says the reaction favors product. If this were negative, it says the reaction then favors reactants. And they can't both be right. Just a reality check. Okay. So here come those bad words again. Homo and hetero. Homogeneous means same. Everything's the same. In terms of equilibrium, that just means that all the phases are exactly the same. Gas, 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 gas. Or, in this case, aqueous, aqueous, aqueous. Or if they were solid, 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 or liquid, 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 they would all be homogeneous equilibrium. As opposed to heterogeneous, in which you have different phases. So there's a solid here, and a solid there, and there's a gas there. There's a gas, gas, liquid. So those are heterogeneous equilibrium. Okay, here's another fly in the ointment. When you're writing an equilibrium expression, don't have to include pure phases. What I mean by that, this is solid. It has no concentration, right? It just reacts until it's gone. Right? Concentration is non-existent. Right? As you use more solid, what happens to the concentration of the solid? Nothing. It's pure. Right? Right? So we just leave those out of the expression. This one's gone, that one's gone. This one does change in terms of concentration or partial pressure. In this case, we're using partial pressure. So that's why the K value is only written in terms of oxygen. If you want to look at it another way, just say, all right, these solid phases are embedded in the K. Either way works. It doesn't change the K value. But if it helps you deal with it, fine. Otherwise, just learn the rule. Don't include solids. Also, don't include pure liquids. Like the one before. That's a liquid. And we're making hydrogen gas and oxygen gas. So you see, I got to balance this thing. I need two of these. So our equilibrium expression here, in terms of molarity, would just be H2 squared O2 to the first power. No water. It's pure. Okay?
So you just draw.
That's it. You only have a numerator in this one.
This is only for heterogeneous.
Heterogeneous, yes. Only for heterogeneous.
So if you have a solid and a homogeneous.
If you, right, you wouldn't have an expression. If it was solid plus solid yields solid plus solid, there would be no equilibrium expression. Yeah, I'm glad you brought that up because I've never considered that before. But true, yeah. It would just be one. Right? K would be unity. Because if you put them in there as anyway, as solid, then they go away. And the expression divided by the same, well, I'm digging that hole deeper than I want to be. So for heterogeneous expressions, you just ignore the solids and the liquids. Keep the gases and the aqueous. Or, well, for our purposes, aqueous, but for chemists in general, anything that is dissolved in another liquid has a concentration, so it would be considered if you used a different solvent. But we're not going to do that. Anytime we have a solution, we're going to put it in aqueous solution. Okay. So we talked about this earlier. If the value is much larger than K, that means equilibrium is, at equilibrium consists of mostly products. And if it's very, very large, the reaction essentially goes to completion. That is, you have such little reactant left, you can say, okay, it just goes all the way. Kind of like hydrogen reacting with oxygen in a space shuttle engine. You got water left over and lots of energy. You don't have any more hydrogen and oxygen. Assuming that you meter them properly, right? You don't have a limiting reactant. Very small K is just the other direction. Mostly reactants, which means that the reaction doesn't want to go. Very small number means it doesn't want to produce products. If it produces any, they're so small, you can basically say that the reaction doesn't go. Now, what if we flip the reaction, reversed it? Then we would reverse the K, and it would be a huge number. So a reaction that doesn't want to go with a small K does want to go if you reverse it. Okay. If the equilibrium lies to the right, the value of K is large, 1. And if it lies to the left, the K is small, less than 1. New concept, sort of. Q. And that has nothing to do with Star Trek, Next Generation. Watches it. Okay.
Actually, I do. My dad watched it still.
Okay. The Q continuum, and I forget the actor's name like that. He's always messing with Picard, you know. Anyway, Q in terms of equilibrium, Q is not equilibrium. It looks like equilibrium expression when you write it. But the D and then A and B.
The only difference is equilibrium.
Right, it's not an equilibrium, and we use parentheses. We use parentheses for concentration units like molarity. Right. We know that in these terms, we're not talking about partial pressures. Right? Otherwise, I'd put a piece of the A. But the Q is the, rather than the equilibrium constant, it's the reaction quotient. Hence the use of Q, the reaction quotient. And the calculation that you do is before the reaction starts. You put in the values of the concentrations of reactants and products. Okay? So if you mix some things together, you mix A and B together, and you say, all right, well, I want to put some C and D in there also. So you go ahead and put both of them in there. Then you do the calculation, and Q will be different than K because you haven't reached equilibrium yet. But the relationship of Q to K tells you which direction the reaction wants to go. Okay? So if Q is greater than K, what does that mean? If Q is greater than K, that means we have more of this and less of that. More product. Right? If it were K, it'd be a certain value. But the only way to make Q bigger than K is if we increase products, decrease reactants. Okay? So that's this situation. And if you have more products than you need and less of the reactants, which direction is it going to go? Back toward reactants. So it's going to shift to the left. Okay, does everybody see that? Okay, so what if, let's do this one just for giggles. If you find out that Q, calculating Q equals K, you're already there, right? So that's no movement. If you're already at equilibrium, you're not going to see a change in concentrations. And then the other possibility is Q less than K. If Q is less than K, the only way we can do that is to reduce products, increase reactants. So that favors products. Moving to the right. Okay? Now just notice something. You write it this way, Q greater than K, the reaction shifts to the one that's bigger. Like that one greater than K. If you write it this way, then the reaction shifts this way for the bigger one. If you write it this way, it shifts toward the right in terms of the reaction as written. Okay. All right. Oh, I gotta have that slide. Okay. So that's got everything up there that I just put on the board. Okay. So let's determine the equilibrium constant for this reaction. Aqueous, okay, so we do include that factor. That's iron 3 ion. What's this one? You may not know that one. It's one of your polyatomic thiocyanate. And they combine to do that. Now, just a comment about the reaction. This looks to me like it's a net ionic reaction. We don't have any counter anion for this one or a counter cation for that one. And if they're just in there by themselves, then that sort of defeats the purpose. Right? Because you want to start the reaction with them separate. So in order to have them separate, you need an anion for this one and a cation for that one. And since those are spectators, we just crossed them out and left us with this one. This is, we'll have the K for this one actually is that formation constant. Because everything is still in solution. And we want to find out what that K is. So let's write our expression. Okay, is this balanced first? One of these, yeah, it's balanced. Notice that the charges are balanced also. 3 plus and 1 minus gives you 2 plus. Okay. So let's write the expression. And they all have coefficients of 1, right? That's convenient. Okay. So we're given these values. At equilibrium, concentration of this, let's see, this one and this one are mixed at a certain temperature. Oh, okay. Here. We're actually doing an equilibrium problem. So we're starting out with a certain concentration of this and this, and none of that. All right, so I need to build an ice table. I also need to define what ice means. Ice means initial change equilibrium. Here's what it looks like. I like to write out the equation and then build my table underneath, like this. And I don't have to write those things again. So our table is going to look like this, this, and that. So what are the initial concentrations? Well, iron 3 plus is 6 molar. Thiocyanate is 10 molar. Okay? How much is iron thiocyanate? That's at equilibrium. Not initial.
Not zero.
Right, it's 0. Okay? Now pay attention to the words. Okay. So which direction is it going to move? Well, obviously, that way, because there's nothing there. Right? So this refers to the change. So what will be the change? Well, we're going to lose some of that and lose some of that and make some of this in a ratio of 1 to 1 to 1. Right? So we're going to add some over here, and we're going to lose the same number, like 1 mole, 1 mole. Right? So we're going to lose the same amount of that. But we're also going to lose the same amount of this one. Everybody see that? Based on the coefficients, if we add a certain amount here, and this is in molarity, we're we're going to add a certain amount here, then we have to subtract the same amount over here. But we also have to subtract the same amount here because it's 1 to 1. And that's the change. We're subtracting here, adding there. So now, let's see. Okay, so this one is actually X. And that concentration is 4 molar. Okay? I'm going around the barn several times, but I want to use the ice table to draw this conclusion rather than just jump right to the answer. I want you to see where it came from. So we add this X, but we're also told that the X is equal to 4 molar. Okay? So that means we lost 4 molar here. This is equal to 4. So what's this one equal to? 6. Right. And that means this one would be equal to 2, right? Okay. Now that we know the equilibrium values, we can calculate the constant. Right? So it's product 4 molar to the first power divided by the product of these two. Okay, so it's 4 divided by 12, right? So that's 1/3. With no units. There we go. Yeah, I must have added one here. This is the correct significant figures. Any questions? Okay, that's how you use an ice table to determine that. And if we didn't happen to know what this value here is, we'd be stuck. Because our equation then would have x's in here, right? We'd have 6 minus x would be in there, 10 minus x would be in there, and x would be in there. And we couldn't calculate this. But if we had that expression, plus we knew what the k was, then we could solve for x and find out what this is. Okay? So let's use what we know here to find out what an unknown concentration would be at equilibrium. So we know our K is 0.33, and let's just leave our table intact and remove the values. Okay, got the same reaction. Initially, we're starting with 10 molar iron and 8 molar thiocyanate. 10 molar, 8 molar. Initial concentrations, and since we're not given a value for this one, we have to assume it's 0. We're starting with 0. But we are given K, and the question is, what is the equilibrium concentration of this one? Okay. So here's the point where you choose your X wisely. You choose your X so that it, if at all possible, solution for the X is your answer. Right? So we're gonna have to add since there's 0 there, we're going to get some x over here. And that means there's our x, our unknown concentration of this ring. So now we can work with the rest of it. Minus x, just like before. So this one is 10 minus x. This one's 8 minus x. And there's x. So now our k, 0.33 equals k equals this concentration to the first power divided by this one times that one. There's our x's. And they're all to the first power. So now we can solve for x. Anybody see a problem with that expression? Solving for x? Yeah, what's going to happen when we multiply those together?
From the
There's another Q word.
quotient.
Quadratic. You're going to have a quadratic expression. Does everybody know how to solve a quadratic?
The formula.
Yeah.
E plus minus. E squared plus minus.
I put it on the back of my calculator, so I wouldn't have to think about it either. So, if our expression is ax squared plus bx plus c equals 0, then the solution for x is minus b plus or minus square root of b squared minus 4ac over 2, all that over 2a. Now, sometimes you have to use that once we expand this polynomial. But sometimes in chemistry, we can say, maybe that x is so small that we can just eliminate it. Right? If the change is so small, but let's look at this and see. This will tell us whether there's going to be a large enough shift where we cannot ignore the x. Right? 0.33. Looks like we are going to get some significant amounts over here. So we're probably going to have to use the quadratic equation.
If you use the quadratic equation, move your A, B, the iron 3, you use 10 as A.
Oh, you won't know that until you expand the expression. Yeah. So let's do that. X on top, and on the bottom we have x times x is just x squared. And then 8 times 10 is plus 80, right? And then in the middle, we have minus 8x and minus 10x, so it's minus 18x. So now there's our A, B, and C. Except we still got an x up here. So what do? Well, you have to take this whole thing to go over here times 0.33. What's a third of 18 is 6, isn't it?
Yeah.
Right. And then a third of 80 is, I don't know if I can do that one with my head. Wish it was 90. I have to multiply it out. 26.4. Still positive. So now this was over on this side equal to x. Right? So it's still equal to x here because this all came over here times that. Now that expression is equal to what left behind. There's x. So now we have to set everything equal to 0. Right? So this x has to come over here minus x. So 0.33 x squared minus 7x, right? Plus 26.4 equals 0. Now we can solve it using the quadratic.
Where did 7? There's one more x on the right.
Yeah, this x right here,
below.
it becomes a negative on this side.
Oh,
Didn't think you were ever going to have to do algebra again, right? Surprise. Okay. So that we don't have to, let's see. Okay. These are a little bit off because I was using 0.33 instead of 0.333. But our x is going to be pretty close. So what you'll end up with in this quadratic is two values because you got plus minus here. Then you have to decide which one's real. Right? So one of the possible answers is 1599. So can we get 1599 out of 10 or out of 8? No. There's not enough material to give you 1599. So it has to be the other one. It has to be 5. So x equals 5. Molar.
At least this has a practical use where you're not just finding random numbers for no reason.
No,
So we were doing an algebra, was just finding random numbers that didn't even need them for anything.
Oh, I
So
see.
at least we need it for this.
Yeah, yeah. I see your comment then. That's true. So if we look back and say, all right, we know that x is 5 because we solved it that way. If we had gone in and said, x is too small to deal with, so just throw it out, right? And then this would be 10 times 8 or 80. And 80 times 0.33 is not 5.
So no negative number in the equilibrium part. That's why you just put 99.
Right, 15.99. If that's x, that means this had to be x too, 1599. So if you say 1599 subtracted from 8, you got a negative number. That's what you were saying. Yeah. Right, there's not enough material to give you 1599. So you have to go with 5. Now, in the future, what do you do if, how do you know, or how do you suspect, let's put it that way, suspect that x is small enough to ignore? That's a very small number. That's a very small number, and you're probably not going to get much x. And you could ignore it, do the calculation. And then how do you know that your answer is close to what it would be for the quadratic? You use that answer and you plug it back in this expression right here, where the x is still there. Calculate it out and say, does it come close to the k value? So at that point, you need a rule, right? So how close is it? How far away from the k can it be and still be acceptable? Well, we use the 5% rule. If the value you calculate with your x, after you've done that sleight of hand, is within 5% of this value, then it's acceptable. And we'll do one. So here's another one. We just run through the procedure again, just like before, just like this, and the value is, in that case, is 3 molar. Now, what does that mean? It means that our equilibrium constant did not change, but our equilibrium position is different. Right? Instead of 5, we got 3. Why? Because we started off with a different amount. So, same, k is a constant, equilibrium position can be anywhere. But it's based upon the k expression. Okay, so this is just sort of pulling things together in one slide. What do you do when you're presented with an equilibrium problem? Same thing you do with any other problem. You write the equation and balance it. If it's not already balanced. If it's not given to you, balance. Then you write the equilibrium expression in terms of the law of mass action. And recognizing that it can be used as a Q determination as well. Right? Same expression, just different place, starting point. Equilibrium expression is valid for an equilibrium system. Right? But a Q value is valid only for a non-equilibrium system. But they're written the same way. Then you list the initial concentrations, calculate your Q, and determine which direction the reaction is going to go. So the only way you can do that here is if you know what K is. If you don't know what K is, then you have to be given equilibrium conditions. Right? Just like we calculated that first problem with the ice table. Right? Q doesn't help you if you don't know what K is. You got to be able to calculate K or be given K. Then the Q will help you. Of course, do we need to calculate Q every time? If one side has no values, then we know which way the reaction's going, right? So I just eliminate Q. Q is only valid if you're given initial conditions where you have concentration of reactants and products at the same time before the reaction starts. Then Q is used to tell you what direction to go.
So the last problems we did, we need to find Q for that.
No,
They start with
We had
0.
0 at the end.
right. The product was 0.
Okay. So the only time we need Q is if that's that on the ice table, that one comes in.
Right. And then this, we're setting up an ice table in here. And you choose your X wisely. If you choose an X unwisely, you can still get the right answer. It'll just take you longer. Because once you get X, then you got to say, all right, what does X mean? How is it related to the answer? Then you have to do another calculation. That's why we want to choose X to be the answer, if at all possible. Okay. So these are 3 more trials. I'm not going to mess with them. Right. You can do those. You have plenty of opportunity in your review document to do ice tables. So we just set it up the same way. Have to use a quadratic because of that value right there. Oh, there's another way to do it also. Rather than eliminate that little X because we say it's too small, it doesn't matter. The other way you can do it is you can say, okay, I know that the first answer is going to be wrong, but it's going to get me like in the parking lot. And then you take that answer and go back in and substitute it for those little X's and solve for the X on top. That gets you a little closer. You know, now you're in the grandstands. Okay, you do it again, and that puts you on the field. And it might take you one more time, and that gets you to the goal line. You got the answer. That's called, let's see, there are a couple of names, actually. One is successive approximations. So you use the answer of one approximation as your starting point for the next approximation, and you get closer and closer until you meet the 5% rule. Once you've met the 5% rule, you can stop. Okay. Let's see. I want to be sure I don't leave anything out. Okay, we're good. All right. Let's see if we can. Now this one is the reverse, right, of the Haber-Bosch. Here we're decomposing ammonia into nitrogen and hydrogen. But is that balanced? So it's not balanced. Right. 3 hydrogens, 2 hydrogens, 2 nitrogens, 1 nitrogen. So you have to balance it first. Let's go ahead and do that. Okay. So I think we need 2 here, make 2 nitrogens, but that makes 6 hydrogens. There we go. Now it's balanced. And the K expression would then be products to the first power, hydrogen, third power, and ammonia, second power. Okay? Now, at equilibrium, 1 mole of ammonia remains. So we start off with 2 moles of ammonia. Let's see. We start off with 2 moles in 1 liter equals 2 molar. And that's where we start. And we don't have any of this. So we know the reaction headed that way. At a certain temperature, the ammonia partially dissociates according to this equation. Okay, we've got that. And at equilibrium, 1 mole of ammonia remains. So at equilibrium, we've got 1 mole left over in the same volume. Right? So it's 1 molar. Okay? So what was the change? We lost a molar, didn't we?
Wait. I get the one. I know. Oh,
This one? It says we have 1 mole left over of ammonia.
oh yeah, it's right there.
Yeah, and the size of the container hasn't changed. Right? So it's 1 mole per liter. Okay. So if we got this remaining, then we had to use that much. Right? We start with 2, we're going to end up with 1, we had to use 1 of it. That also tells us how much of this we get. So if the ratio is 2 to 1, how much nitrogen do we get? Half as much, right? Going from 2 to 1, get half as much. And this one is a little different. So we got 1 like that. Hydrogen. Coefficient here, 2, 3. So it's 3 halves, or 1.5, right? Everybody see that? Okay. So that means at equilibrium we have this and this. And now we're just plugging in the expression. So nitrogen is 0.5 over the first power. It would be consistent. And hydrogen is 1.5 to the third power. And then ammonia, left over at equilibrium is 1. What's K? Well, let's see, my brain is not that good. So 1.5 to the third power. So this one is 3.375 times 0.5. 1.6875 divided by 1. Something like that. Okay. Round it off, 69. Okay. So I guess the moral of this story is when you set up an ice table, you don't have to be linear about it. You don't have to go blank, blank, blank. Set up your ice table and put in the information that you know, that you're given. Then you might have to sort of work backwards to fill it in and prove to yourself that that equilibrium position is valid.
And the reason why you put 0, 0 for those because he was given to you. So you could feel it.
Right. A 2-mole sample of ammonia is introduced into a container. The ammonia partially dissociates. It doesn't say anything about these concentrations, so you have to assume that they're 0.
So where did 0 come from?
The 1/2.
Right. You got 2 of these, you only got half as many of those. All right. Let's see. This. Yeah, it's a different reaction, so we erase the whole thing. All right. So this one says, here's our reaction. It looks like it's balanced. 2 nitrogens, 4 oxygens. Okay, we're good. The K value is given to you. 10 to the minus 4th. So it's written which side is favored. Yeah, this side is favored. Right. So the conditions we're given are 1 mole of N2O4 in a 10-liter vessel, allowed to reach equilibrium, which means there's none of this to start with. They're both gases. So we have 1 mole in a 10-liter vessel, which is 0.1 molar. That's 0. This is the initial condition. All right. Let's see. The K value, we'll get that in a second. What's the equilibrium concentration of each one of these? Right. In this case, you're given a K. Right. So the equilibrium concentration, since there's none of this one, I would say, let's make that our X. Right. Then if we know that this is X, then it's just a matter of subtraction to find out what this is. Well, actually, it's coefficients. Excuse me. Use coefficient. All right, so what's the change? Well, this one added X. Where did it come from? Well, if this is 2, then this one has to be a half an X, doesn't it? Because for every one of these, you get 2 of those. Yep. Because if this is X, NO2,
Oh, is it because N2O4 is 1 of 2?
yeah, this is 1, this is 2. So it'll be half X for this one. That means 0.10 minus 0.5 X. And then our expression is just that one, our K, is NO2 squared divided by N2O4. So now we have values. So we put this one in here, and this one in here. Like that. To the first power. And that's equal to oh, yeah, 4 times 10 to the minus 4. There we go. Now, the question is, we've got an X squared in there, so we got another quadratic. do we need to keep this x? Let's factor everything out first. Right? So this would be x squared equals that expression times this expression. So 0.1 times that is what? 4 times 10 to the minus 50. Because this is 10 to the minus 1. And then minus 4 times a half is what? 2 times 10 to the minus 4 x. Okay. Now, if x is really small, then we should be able to say that x is 0, and that term goes out. And then x, we know what that means, approximately. X then would be the square root of just this term. Did I lose anybody? I'm saying that this term, because x, I'm assuming x is very, very, very small, then this term just goes away. Then we're only left with that term. So let's see. Square root.
632 times 10 minus 3.
Minus 3. Oh. Now, what we need to do is plug in this value for x in here and here and see if it's close to that. Right? So we're going to calculate a k that may or may not be that one. Actually, no, we're not going to calculate k. We're going to set it equal to 4 times 10 times 4. And then say, is it equal to the expression? So if we say 6.32 times 10 to the minus third squared over 0.1 minus 0.5 times 6.32. That, then what do we get? Okay, so this one squared is, here it is. Well, this one squared is that value. Duh. Because we took the square root of it before. And then we're going to multiply this one, 6.32 exponent. Subtract from 0.1.
I got 4.124 times 10 to the negative 4.
4.13.
3.12458.
Okay, yeah, because yeah, I kept the old unrounded number
Oh,
here. That's okay.
I didn't have.
We're close enough. Yeah. So this is 4.13. I have times 10 to the minus 4. 10 to the minus 4. Right. So it looks pretty close. Let's see if it matches the 5% rule. So what's the difference? 0.13, right? And you don't have to include the exponents. 0.13 divided by 4 times 100 is equal to, we could include the powers, but there'd be power on the bottom, power on the top, they cancel. Right? That's why I can use that. So 0.13 divided by 4 is 3.25%. Good. So our approximation worked. Oh, excuse me. That was X. So the concentration of, we would have to plug in X here, right? 4.13 times 0.5 exponents times 0.5. And then that's subtracted from 0.1 would be 9.98 10 to the minus 2 more. Close. And then this one would be the X value. 6.32. This is X. Would be that. Okay? I know that's a lot of work for just a couple of answers. So the moral of this story is do a lot of them until you feel comfortable with the ICE. The ICE procedure. Okay, next week's lab is based upon the Lecture2020 principle. He was a French guy, of course. We've actually already discussed Lecture2020's principle in a roundabout way. A system at equilibrium, when disturbed, will react in such a way as to mitigate that disturbance. Okay. Another way to say it, if a change is imposed, the position of the equilibrium will shift in the direction that tends to reduce the change. So that's like our previous one. You add water, shift that way. If you add hydrogen, shift back this way. But the Chatelier goes a little bit further because our previous examples were based only on concentration. So if you change the concentration, you get a shift. Right? We know that. Sure, I spell it right. Okay, so in terms of one, concentration, the effect is if you increase the concentration, the system at equilibrium, if you increase the concentration of products, it shifts back toward reactants. Or if you increase the concentration of a reactant, it shifts toward products. What if you remove some of the product? You decrease its concentration, so it shifts to the right. In the Haber-Bosch process, we have N2 plus H2 yields ammonia. We have 2, 3. Right, these are all gases. So as the reaction goes, the system is set up for removing some of the reactants and products together. Just suck them off. Run them through a chiller where the temperature is just cold enough to condense this one, but not cold enough to condense these. Right? These, you have to get really, really cold to drop these out of solution. I mean, out of gaseous phase. But you only have to get it slightly cold to condense this one. And you remove this one, and then you take what's left over, run it back through the reactor to go again. you go those repeated cycles. Eventually, you get a very high efficiency. But in that case, we're removing product, which means the reaction shifts this way. Okay? So what other possibilities are there? What happens if you change the temperature? Say again? Yes, the K will change. And it will depend upon the delta H of the reaction, the enthalpy of the reaction. So if you have a reaction between going from A to B, just to keep it simple, and the delta H is a negative value, what does that mean? It's exothermic, right? So it gives up heat in the process. So what happens, here's the way I like to look at it. For this one, write it like this. Plus your heat. That's me, sorry. I'm due for another dose of coffee. So if the heat is released, it's one of the products, right? So if you write it like that, an exothermic reaction written where heat is the product, then it's easier to tell if we increase the temperature, we're adding heat, right? Increase the temperature, add heat, the reaction shifts back that way. So what would it look like if it was endothermic? Delta H is positive.
It would be the A plus changing.
Right.
A plus changing.
Exactly. Now, if you add heat, you're favoring products. Okay. Pressure. Right. This has to do with any reactions involving gases, of course. Because what effect does pressure have on liquids and solids? Nothing. Plus, they're not part of the K expression anyway, right? So you only have to consider gases if there is a gas in the reaction somewhere. Okay? So, how do we change the pressure without adding more reactant or product to it? Because then you complicate it. If you add more reactant or product to it, then you're back to this situation, plus this situation. Right? So we want to study gases in terms of change in pressure without changing the number of moles. So one way is to squeeze them, decrease the volume. Right? So if you decrease the volume for a gas reactant going to a product, if you've got the same number of moles of gas on both sides, and this can be multiples, right? Just add them up, add up the coefficients. This is 1 to 1. If you've got the same number of moles of gas on both sides of the reactant, increasing or decreasing the pressure has no effect because it does not change the partial pressure of either one, right, to the same ratio as they were before. But let's say if we have, this one gives us 2 of these, and you increase the pressure. The response of the system is to mitigate that increase in pressure, and how does it do it? It uses Avogadro's law. You decrease the number of moles of the gas, and that alleviates the pressure. Right? So if you increase the pressure on these two, decrease the volume, then it's going to shift this way. Right? But if it's the other way around, increase the pressure, it's going to shift that way. Okay? So So it's the difference in number of moles. If you have a change in moles, remember we calculated that delta N? If your delta N is 0, pressure has no effect. There will be no change. Sounds like a good test question. Write that down. Okay.
So if delta is 0, no change, and there's nothing to do with pressure.
Right, if delta N is 0,
stress. If reactant or product molecules are added to a system at equilibrium, the system will shift toward the side opposite of the added component. If a reactant or product is removed, the system will shift toward the side of the removed component. Let's consider an example of a system at equilibrium, the reaction between iron and thiocyanate to form iron thiocyanate. Iron 3 is a light-colored ion in neutral or slightly acidic solutions. Thiocyanate is a colorless ion in solution. The iron thiocyanate complex is a blood red ion. The reaction of iron and thiocyanate in solution is reversible. That is, it moves in both the forward and reverse directions. Let's consider what happens to the reaction when changes are imposed on the system. In which direction will the addition of iron-3 nitrate shift the equilibrium of this reaction? Observe what happens as iron-3 nitrate is added. The equilibrium shifts toward the product, since the iron-3 nitrate is a source of iron-3 ions, one of the reactants in our equation. As a result, more of the iron thiocyanate ions are formed and the solution turns redder.
okay, you guys get to do that one in the lab.
That's what we're doing in the lab. You said.
One of the things.
The equilibrium between dinitrogen tetraoxide and nitrogen dioxide is dynamic. As shown, N2O4 molecules fall apart at the same rate that NO2 molecules recombine. If we change the equilibrium conditions, the equilibrium concentrations will shift according to the Chatelier's principle. As we increase the temperature, the equilibrium shifts to the formation of additional NO2 molecules.
Yeah, he talked about that thing for sure, right here.
It was different from the study guide.
It was, for sure.
Beyond the student version of these whole tests. Just
About 4 questions with about.
I got this. I got that one too, and it was awesome. Like this.
Well, it wasn't a whole lot.
Like I said,
I wanted to get I calculated all my freaking orders I got right. 22, 24, but then I added 15 because I got 3 days right. It's great.
when you look at activation energy, it goes from reactants to the top of the thing. So it'd just be the one that goes from this line up to this dotted line. So it'd be- And that's without a catalyst. With the catalyst would be from this line to the top of the end. And then the reverse reaction would just be from this to up there. See.
Sorry. Don't know my own strength. Oh, that's it. Okay, so next week we'll review chapter 13. That's the only chapter on the next exam. And go in the lab. be sure and have your, well, let's see, you won't have to put this procedure in your lab notebook because it's not a formal report. That doesn't prevent you from doing it. In fact, it'd be nice if you would.
Just not necessary.
Yeah, I shouldn't say that really because I know as soon as I say that,
Nobody in the class.
half of you are not going to read it. That would be a disaster. Because there are some hazardous materials in this lab. We have to use a cube for a couple of steps. Concentrated hydrochloric acid.
The fixing as well, right? No.
Hydrochloric acid, it'll choke you.
Yeah. The fume can fix from odor.
Yes.
You can only chuck it for so long before you die.
Well, yeah, look at it that way. Look on the bright side. I'm dead.
Yeah, they can only chuck you for so long.
Okay, let's shut this off before more foolishness is recorded.